Спасибо.
Так, все-таки нет.
Okay, so last class we discussed base point free devices. So such devices that for each point there is a section which doesn't vanish at this point. I don't know whether you know why is it so useful. Знаете, зачем нужно разгрузить на строчку?
Нет.
Хорошо, ладно. Okay, so what did we prove? We had that the divisor is base point free if and only if m sigma is in our polytope for all sigma. So, сейчас мы были в прошлый раз?
Нет. Ну, я посмотрел.
Хорошо. Окей. So, roughly speaking, each section is in some sense a coordinate. And if we take, we know that in our case, OXD is finitely generated under some restrictions. And so if it is finitely generated, roughly speaking, you take several sections and they give us a map to the projected space. Okay? And it is, if we want it to be everywhere defined, at each point we should have at least one non-zero coordinate. So if we have a divisor such that XD has enough global sections, then we know that they are given by some characters, M1, etc. MS. Such a construction, chi M1, chi M2, etc. will give us a map. In some points, so chi is defined on a torus. Maybe it is not well defined on the whole variety. Maybe it will vanish when we take the closure, but roughly speaking, this gives us a map to the projective space, and we need to have a non-zero section at least at each point. Okay, this is what we will use, and now we can generalize it in some sense. So, what do we want? First, let us say what is a convex function. Do you remember our function phi d? It was a piecewise linear function. It was a function from our fan to real numbers, or maybe to this transit over q to q, it doesn't matter, which was linear on each sigma and sigma. And if our divisor is the sum AIDI, these are Toric invariant divisors corresponding to the arrays of our fan, then we wanted phi d on u rho to be equal to minus a rho. So, for example, this is our fan sigma. We have u rho 1, u rho 2, u rho 0. So we want this piecewise linear function be linear on each cone and take values minus a1, minus a2, minus a0 at these points. You can set these values and then reconstruct a function. What about base point free divisors and corresponding functions? What is a convex function? For us, we want it to be convex in this sense. So phi from the intermediate point it should be greater or equal than t phi x plus 1 minus t phi y. Okay? We want to show that if the divisor is base point free, then its support function is convex. This is our aim, but first we will need several technical statements. The first technical statement, and we always assume today that our fan has convex support and that it is of full dimension. For example, we should forbid such a fan. It is not if we don't have these cones, this is not a convex set. This doesn't work for us. Convex support and full dimension just to have a good toric variety without cis-2 factors. Okay. So, the following lemma. I think I will check it because the ideas of the proof will be necessary all the time. So the first is, so we always have sigma, we have B, a Cartier divisor. First,
this is just for the lemma 2 hour. These will always be a Cartier divisor.
All the time we will be a Cartier divisor. So phi D is convex. But right now we will not use the divisor. We will use what we know about divisors. So this lemma is purely from convex geometry. B, the function phi d, phi du is less or equal than m sigma u for all u and for all sigma. u is taken from this, and sigma is taken from n-dimensional curves. Do you remember that we know that phi d is piecewise linear, so at sigma it is given by the scalar product with some m sigma. M sigma is the data given our function phi. Еще раз сказать? Да, можно. Смотрите, мы сказали, что функция фи d кусочно-линейная. Ну, вот на такой штуковине просто. Как задается линейная функция? Это элемент как бы двойственного пространства. Ну, то есть, по факту, это какая-то точечка m сигма. Если мы считаем, что наша функция целочисленная, то есть на решетке принимает целое значение, то как бы этот элемент двойственного пространства лежит в двойственной решетке. Вот, поэтому здесь m сигма, как бы, грубо говоря, здесь свое m сигма, здесь свое m сигма. И если мы смотрим на вот эту штуку, у нас есть вольность в чем там, в ортогонале. В смысле, на таком луче задать линейную функцию можно скалярным произведением с m сигмой с точностью до элемента, который вот так вот. Прибавлять элементы из ортогонала мы можем, они на этом луче значение нулевое имеют. То есть, когда мы говорили, что у нас есть разные m сигма, у нас есть здесь m сигма, здесь m сигма, но как бы если они разные, то их разность зануляется на луче. То есть сидит в ортогонале к этому лучу. То есть фи d это кусочная линейная функция, а чтобы задать кусочную линейную функцию, нужно ее задать на всех максимальных конусах. У нас максимальные конусы все, наверное, полной размерности. Все полной размерности, иначе как бы у нас будут проблемы с выпуклостью вон там вот. Okay, this was the second part. Now the third part. You should follow attentively. Phi du is in fact the minimum of a finite number of linear functions. Minimum is taken over all sigma from n-dimensional curves. The scalar products of m sigma and u for all u from what about sigma. And the fourth it is very useful in proofs. For every wall, so tau is the intersection of two cones of dimension n. There exists some vector from sigma prime without sigma with phi d u0 less or equal than m sigma u0. Okay, so this is our sigma prime, this is our sigma. This will be u0, it will be here. So the function here is given by the scalar product with m sigma prime. So, and this will be if we extend this m sigma to the neighbor cone. So these are four statements. I want to show that they are all equivalent. It is not very difficult. Once more, there is no toric geometry. There is only Cartier data, and that's all. So what is obvious? What is obvious? So first, why A implies B? Take sigma and find some vector v in the interior of this cone. Okay? And take any u from our fan. Then there is always, so if u is in this cone, there is nothing to do. It is equal to m sigma u. If u is somewhere here, at this segment, there is a point close to v. So it will be close to v, so it will be in the interior of sigma. And let us write the convexity condition. Phi d at this point, it will be since it is in sigma, it will be given by m sigma t moment, let it be tu plus 1 minus tv. Okay, this point is in sigma, so phi d is given by this scalar product tu plus, it will be greater or equal t phi d u plus 1 minus t phi d v. Okay, this is linear, and this is the scalar product. M sigma and v. Okay. So one minus t m sigma v, 1 minus t m sigma v, this and this goes out. Then we divide by t and we obtain m sigma u greater or equal than phi d u. Okay, what we wanted. Then B implies C. Suppose that B implies C. So if we take sigma containing U, then this will be equal to the scalar product. And so phi d u will be equal to one of these values, and it will be less or equal than all the other values. Okay? So B implies C when we take sigma containing our point U. We suppose that we fix U. We want to prove this for U, and we find sigma, and we choose the one which is the minimum. Okay? Do you agree? Okay. What next? Then C implies A, because we have a finite number of linear functions, and their minimum will be convex. Okay? Just a minimum of a finite number of linear functions, it is convex. Okay. So now A, B, and C are equivalent. Then also, so now we have Also, it is clear that B implies D. If this is true, then this is also true. Okay. Let us show the converse. That if we have only D, we can reconstruct all the other parts of this lemma.
А вот в
Да.
С у нас минимум берется по всем конусам или если...
В смысле, это конус максимальной размерности. У нас хороший веер. Много говорить про скобок. Если мы объединим как бы замыкание всех конусов максимальной размерности, мы получим, точнее, если, ну да, далее, с границами берем, это будет весь носитель веера. И это будет выпуклая штука. Поэтому в С просто конечное множество вот этих вот М-сигма берем. В смысле, М-сигма — это элемент двойственного пространства. Так у нас в веере конечное число этих конусов максимальной размерности. Мы же не брали такие бесконечные вееры, когда мы там режем. Это не в нашей науке. Okay. I think I should add a page. What if we have only D? So assume now D. So we have tau, we have sigma prime, sigma, and we have tau. And let us fix them. We know that it exists U0 such that phi d U0 is less or equal than M sigma U0. Okay, let us prove something from the previous statements. What is tau? Tau is a wall between two currents of dimension n. So it is of dimension n minus 1. It is given by some equation. And there are two cases. If M sigma equals M sigma prime, then B is true. If they are not equal, then if we write M sigma minus M sigma prime U equals 0, it is the equation defining tau. Okay? We said that if they're distinct, they differ by an element from the orthogonal. And so it is unique up to a constant. And if there exists some equation defining tau, so here it is. Okay, and we know that if we write an inequality, then it will be it will give sigma prime or sigma. So on each sigma prime we have one sign, and on each sigma we have the other sign. Which is the correct one? We know this. So this is m sigma prime u0. So if we write such an inequality, it will now define sigma prime. Because we know that at u0, the sign is in this direction. Here we use the properties of the fan. Понятно, да? Веер. Мы сразу определяли так, что веер, что такое стенка. Если есть стенка между, размерная стенка внутри между двумя конусами, то получается, что есть уравнение, которое высекает где-то 0. С плюсиком будет один из наших конусов, с минусиком будет другой из этих конусов. И вот, чтобы определиться, кто плюсик, кто минусик, я говорю, что у нас же было U0, на нем знак такой. Значит, на сигма-штрих вот такое неравенство.
Последнее предложение.
Ну вот смотрите еще раз, давайте рассмотрим знак вот этого скалярного произведения на объединение сигма-штрих и сигма. На стенке это 0.
Да.
С одной стороны
плюс, другой минус.
Да. Дальше что такое пункт D? Что такое пункт D? Что у нас найдется такое U0, лежащее здесь, но не здесь, на котором функция не превосходит скалярное произведение взятого на другом конусе. По сигме взятого на другого конуса. Поэтому если мы... Но при этом мы знаем, что функция кусочная линейная, здесь это скалярное произведение с m сигма штрих. То есть мы получаем, что в точке U0 мы имеем вот такое вот неравенство. Пам-пам-пам-пам-пам. Вот m сигма штрих U0 меньше или равно, чем m сигма U0. То есть вот они линейные, мы их вычтем, распишем, и получим здесь, да, больше или равно нуля. То есть если на одной точке больше или равно нуля, значит на всем конусе больше или равно нуля. Что мы хотели? Что мы хотели? Okay, so we showed that if we have two adjacent cones, then we have this inequality. We wanted to show that we want to show B to show that phi d u is less or equal than m sigma u. Okay. We can we have m sigma. We have sigma, and we have our point u. If it is in sigma, it is obvious. We have equality. If it's somewhere here, then take any point at the interior of this cone such that this segment such that its direction does not belong to the union of all the n minus 1 dimensional faces. Okay? So this segment will intersect all the walls of our cone in one point. It will not belong to any of the walls and to any of the rays. Okay? If this segment intersects each wall in a correct way, then then we know that at each step we have this inequality. So we can write the similar chain of inequalities and obtain what we want. So we have m sigma here, m sigma prime here, etc. Some m sigma here. And in the same way, we say that m sigma u will be greater or equal than m sigma prime u, and so on. And the last one, which is the value phi b of our point u. So we showed that D implies B. Верите?
Да.
Супер, хорошо. Okay, so we are done with this lemma. We have 4 ways to say about convex functions. Okay. Now the next statement. It is still about convex geometry. So the next lemma. Maybe it's difficult to understand its formulation. It says that PD. Do you remember what was PD? It was given by inequalities. M euro greater or equal than minus a rho. If we have some Cartier divisor, it has a rho, and euro comes from our fan. This is the definition of PD. But now we state that PD is we take it over real numbers. And it will be the set of all m such that phi b u less or equal mu for all u from our fan. Maybe it seems strange, but this set of conditions gives us also PD. Let us show this formally. So first of all, take this statement. If phi d u is less or equal than the scalar product for all u, then we can take u rho. If we take u rho, then phi d u rho, it is minus a rho less or equal than mu rho. So this is indeed the inequality which gives PD. Okay, so if this is true for all U, then M belongs to PD. And now, so we have proved that this new object belongs to PD. Why PD belongs to this new object? The other inclusion. If we take M from PD, we mean over real numbers. And any U from our fan. Then U is in some sigma of dimension n. Okay? Our fan is quite good. We can decompose U as the sum of all the rays of this sigma lambda rho u rho, where all lambda are non-negative. Lambda rho. If we know that M belongs to PD, then we know all these inequalities. Okay, and we want to show this. What is now MU? We can decompose this first. U is decomposed in this way, so it is the sum of rho M lambda M u rho. Okay? This is just, we replace U with this one. Now we know that M is in PD, so this is true. So this is greater or equal to the sum minus lambda rho A rho. And we wanted this. But this is exactly phi du. Because phi d is a linear function on sigma. We know its value on the rays of sigma. And if u is inside, if u is decomposed in this way, then it is given by some lambda rho minus a rho. Понятно? Там я не нарисовала картинку, вот это вот была сигма у нас, а в ней сидела ю. А здесь были лучики, по которым мы раскладывали. Вот. Okay, so we are done with the lemma. We show that we have both inclusions in one direction and in the other direction. Okay, then one more statement from convex geometry. Now we can say about devices without base points. So maybe it will be surprising. So A and B is what we've had before. M sigma in PD for all sigma. Then C is, no, this one is not surprising. The next one is surprising. Phi D U is the minimum from the scalar products M sigma U and the last one, phi D is convex. What do we know? We know that I didn't finish, sorry. If sigma is complete, it means that is the union of all the curves, this is the whole space. Then what is more interesting? PD is the convex hull of our M sigma, which we constructed now. So here we say that they belong to PD, and here that they give it. Then the set M sigma is the set of vertices and the last one is that phi D is the other way to look at the minimum for all M P D taken over real numbers, not only the integer points but the real ones too. MU for all U is NR. Okay. The last three statements are only for complete fans. Okay. What have we done up to now? A is equivalent to B. C is equivalent to D. Let us write down something. We know that phi D is convex. Then it is equivalent to phi D U is less or equal than M sigma U for all sigma and for all U. Sigma, the cone dimension, and U from the support of our fan. Now, this is equivalent to M sigma belong to PD, because this is if we take U equal to U rho, as we have done right now. If M sigma belongs to PD, then this is true, and if this is true, then M sigma belongs to PD. The same check as we've done. So D is equivalent to B. Now we know that we assume that sigma is complete, and that first four statements are equivalent. So let us assume B. We know that our fan is complete, so PD is a polytope. Okay? Помните, да? Когда веер полный, то все PD это многогранники, да. Но они могли там схлопнуться, но в целом они не могут быть бесконечными. Okay. So we know that phi d u is the minimum overall sigma m sigma u. Now phi d u is less or equal minimum over all m. This is taken over real numbers. Mu, because if we vary m, then for each fixed u, the minimum will be on some vertex. Okay? So this will be true. Then if we restrict ourselves only to the vertices, it will be less or equal than minimum. One moment. No, so this is true by the other statement, by this one. Okay? Since this is true, then we have this inequality. Then if we restrict to the vertices, it will be the minimum m sigma u, which is phi d u. Okay? So we assumed B, and we obtain G, because we will have equality everywhere. So B implies G. Okay?
Where did you write the last inequality?
I know that the first four statements are equivalent. So if I have B, I also have C. This is exactly what is written here. So once more, this is by the previous lemma. We showed that phi du is less or equal than any scalar product mu. So it is less or equal than the minimum. If we assume that u is fixed. U is fixed, then this is true by the previous lemma. This is true because we choose minimum only among a subset of values. So we know that LM sigma are in PD. This is the minimum over this set of values, over some compact set of values. And this is the minimum over some points. And this is equal to phi du because of C. Что? Я нарисовала, нет, я нарисовала PD. Это PD. Еще раз, здесь минимум берется по всем вещественным точкам в PD, а здесь минимум берется по какому-то конечному набору М сигма. Поэтому не нравится в эту сторону. Просто из тех соображений, что как бы минимум брать по меньшему множеству, это будет чуть-чуть... Да. Okay, but we have phi du on one hand and phi du on the other side. So in between we have equalities. So we have shown G. Верите? Ну да, как бы дивизор D это набор чиселок, как бы ро. PD определялся, вот я его написала, M юрой больше либо равно, чем минус ро. Мы как бы сказали, что если D полный, то это какой-то ограниченное как бы многогранник, заданный как бы неравенствами линейными. Нам надо, чтобы он ограниченный был, чтобы мы вот этот вот объем минимум могли брать по компакту. Вот здесь M пробегает компактное множество. Если бы оно было бесконечно, было бы нехорошо. Оно бы могло бежать в минус бесконечности. Так. Questions? Okay. Then I want to say that G implies D because a minimum of a set of linear functions, it will be convex. G implies D. Okay, so for complete fans, A, B, C, D, and G are equivalent. And now the most interesting that M sigma, in fact, are the vertices. Okay. So, what should we prove? Let us prove that B implies F. Then clearly F implies E, and E implies B. F implies E implies B is obvious. Okay? Just formally. If M sigma is the set of vertices, then PD is the convex hull of these points. And if P is the convex hull of these points, then all these points belong to PD. How can we prove B to F? So we take any sigma of dimension n. Take any interior point U in sigma and let us consider the following hyperplane. The hyperplane we can take the hyperplane H U A, and let us take A is phi D on our point U, just to fix it, just for simplicity. And HUA, it is the set of points here, such that MU is equal to A. Okay. Clearly, U is in this hyperplane. Okay? U is in this hyperplane because MU is phi du, since U is taken from sigma, just formally. And we want to show that it is a supporting hyperplane of our polytope. So a supporting hyperplane is such a hyperplane. Polytope is at one side, and it has some points in common. So HUA is a supporting hyperplane to PD. Why? Because we can decompose U using the rays of sigma. If we write U rho from lambda rho greater than 0, we can write such an equality because sigma was our full dimension, U was an interior point. It means that in this decomposition we have n linearly independent rays. Okay? Внутренняя точка конуса сигма записывается вот таким образом, где обязательно здесь найдется n линейно независимых урошечек. То есть как так всегда можно сделать, это потому что мы прямо из вместе. Okay. Then what about MU? It will be the sum lambda rho M rho and we know that M is from PD. So it is greater or equal than lambda rho A rho. So this is phi du. This is what we set A. Okay? Recall, we group from B to F. In B, we know that all M belong to PD. Okay, so we should No, we. So, with group P to F, we know that all M sigma are in PD. Yes. And now we want to define this hyperplane. Yeah, I want to show that it's important, so I take any F from PD, and I want to show that this sign is constant. Okay? And the sign will be constant. We will always have this inequality. So the sign is constant and we have one point in common. So it is indeed a supporting hyperplane. Okay? And from this inequality, we can conclude that H UA intersected with PD, it is the only point. So, for example, if this is our PD, it can have many supporting hyperplanes. For example, this one is also a supporting hyperplane, and this one, and this one. These are all supporting hyperplanes. But I state that the intersection is the only point. Let us follow. If we take a point from the intersection, then the equality here should be. Okay? When do we have an equality here? When M U rho equals minus A rho for all rho which appear here. But I said that this sum contains n linearly independent rays. So if it contains n linearly independent rays, then this system should have the only solution. And we know one solution, this is M sigma. It is unique, it is M sigma. So we showed this. And and once more, what did we try to show? We know that B is true. We want to show that M sigma is the set of vertices of PD. We showed that each M sigma is a vertex. We took M sigma, then we use U, and we construct a supporting hyperplane such that the intersection is the only point. So it cannot belong to faces of greater dimension. Okay? If your polytope, it is also from convex geometry. If you take a polytope and a vertex which belongs to some other face of greater dimension, then all the supporting hyperplanes will contain the whole face. And so the intersection will contain more than one point. Okay. It is not the end. We show that all M sigma are the vertices, but we want to show that all the vertices appear as some M sigma.
There is no other extra vertex.
Yes, no other extra vertex. What now? Suppose that V in PD is another vertex. So it contains also, so it has a supporting hyperplane. Just because there is a linear function which is of some sign on our polytope, so it will be HUA. Also, the scalar product with U is greater or equal than A. But now A is just any real number. Okay? And the condition that it is a vertex is that HUA intersected with PD, it is only V. Okay. So we know that MV is greater or equal than A. But we know that B was equivalent to all the other statements. So this is true. And this is true. Okay? Let us use it. Let us write phi du. We use that our fan is complete. So HUA is the scalar product with some vector u from the dual space. And so phi du is correctly defined. Phi du, it is minimum over all M from the real polytope MU. But this is equal to MV which is equal to A. Okay? So our U is fixed. U is fixed, and so it is always greater or equal than this one. But also we have phi du is minimum over all vertices, over all cones of maximal dimension. M a sigma U, which is also A. So the scalar product with V is the same as the we want to say that we want to show that this is да. This is VU. Yes. And so VU is equal to A, and sum of these M sigma and U is also equal to A. So V should be equal to 1 of M sigma. So there is this sigma. V is equal to M sigma. And we show that indeed M sigma forms the set of all vertices. Верите или не очень? Да, давайте. Еще раз, мы взяли какую-то вершину, которая пока априори не сидит среди множества m сигма. Мы ее взяли, у нее есть уравнение ее задающее. То есть есть вот это вот, для которого на всем многограннике выполнено неравенство, и в точке V выполнено равенство. Дальше давайте что-нибудь напишем. Мы знаем по определению, что φ d это минимум по всему многограннику скалярного произведения mu. Вот. Мы знаем, что этот минимум будет называться vu. И мы его обозначили А для удобства, потому что мы этого значения в той точке, где мы хотим. Дальше, с другой стороны, мы знаем, что чтобы посчитать φ d от u, нужно взять минимум скалярных произведений с m сигмами. У нас есть некий конечный пул m сигма, из которых мы должны выбирать. Вот. То есть мы получили, что для нашей конкретной u vu равно m сигма u. Из этого мы хотим сделать вывод, что m сигма, что v совпало с каким-то из m сигма. Ну, почему? Скалярное произведение с u, вот у нас был многогранник, да? У нас скалярное произведение с u. Мы знаем, что на всех других точках многогранника оно будет больше. Мы знаем, что все m сигмы сидят в многограннике. Что не могу увидеть здесь. Вот как бы если сюда никто не попал, то мы никогда не добьемся, чтобы m сигма u совпало с vu. Потому что vu самая маленькая, а эти будут стопудово больше. Они будут в сторону лежать. Ну, поскольку мы хотим, чтобы все-таки нашелся такой, значит, v совпало с каким-то из m сигма, то, чего мы хотели доказать. То есть мы исходили из того, что все m сигма лежат в нашем многограннике. Первый пункт мы доказали, что все m сигма это его вершины. А пункт второй мы показали, что реально все вершины мы так получим, без пропусков. Вот. Так. Никто никуда не спешит. So I can estimate that it was more or less the half of this of our lecture. If you have enough thoughts, we will continue right now. Okay? Okay, if you want some pictures, we can draw a picture about the Hirzebruch surface. What about graphs? If our fan is of dimension, for example, 2, then we can write a picture in the three-dimensional space. So this will be our fan, and this will be the value of phi d. Okay? Просто график, конкретно просто уверен, а тут зачем мы пишем? Okay, we have discussed several devices. For example, if we take a divisor D4, then what is added number? It doesn't matter. Okay? Any divisor DI. What is the graph of this map? So 0, 0, 0, minus 1 under 1 grade. So this figure will be convex. It will go down on one direction. Okay? This will be convex. So it will be base point free. The function will be convex, so the divisor will be base point free. And now, now I know D2 and D4. Do you recall what is the fence for the roof surface? It is like this. D2 and D4. Okay? On one line. If we take D2 plus D4, it means 0, 1, 0, 1. Coefficient at D1 is 0, at D2 is 1. At D3 is 0, and at D4 is 1. How do we write a graph? It will be 0, it will be minus 1. It will be 0, and it will be minus 1. So clearly it will not be convex, because this segment will be downstairs and this segment will lie above. Okay? So it means that by the picture it is clear that phi d is not convex. So it has base points. Okay. Now a little bit of polytopes. So suppose that we have a lattice polytope. So it has the vertices are from the lattice. We want to use without proof today that n minus 1 p and all the kp k is at least n minus 1 are very ample. So it means that if we take this polytope for each vertex, if we set it to 0, then these points will generate M intersected with this curve. Do you remember? So I define it by P prime. We want that if V any vertex of P prime, then P prime minus V, it is the shift. intersected with our lattice generates the cone intersected with our lattice. Okay? In some sense, it contains the basis of our lattice, and it contains all the points. It can be done. There is no toric geometry, just some combinatorics. Okay. Okay. Now, what next? Take a full dimensional lattice polytope P. So it can be given by inequalities. It can be given by as before. There is no coincidence. It is just the convex geometry, but it is very close to the toric geometry. U F Вы хотите только экзамен идти?
Ну, вообще, да. А лекция еще идет?
Да, лекция идет. Я буду...
Давайте так.
Нет, ну так середины не очень полезно будет. Okay, so just any polytope can be given in this way. Okay? These are normals to the facets, and these are some values. Okay? So, if we start just with a full dimensional lattice polytope, we can obtain a toric variety. Just if we take P intersected with M, the set of points which we can define M1, etc., MS. And we can just take this closure. Now, one moment. Let us define XP is so if we take KP intersected with M for big P, for big K, we take a K big enough so that KP becomes ample. Okay? So this will give us the set of characters and so as before, this is the construction. We will have two toric varieties. This one, and this one. And so, if we take K big enough such that the polytope will be ample, then it will be a closed embedding to some big projective space. So, XP will be mapped by these characters to a projective space of big dimension. But we have two varieties which will be similar but a little bit different. This one is good, and this one we don't know whether it is good or not. Okay? But we always have a divisor. We have a divisor, dp. So the fan will be the normal fan to this polytope. And the divisor will be given by the same numbers. It will be the sum AF dF. So P is in the lattice M. When we take the dual fan, we go to the lattice N. Okay? And then what will facets go to? They will go to something of complementary dimension. So each facet will go to the normal ray. So for the fan, dF will be the ray. So this will be a prime divisor. So if we started with a full dimension that is polytope, then we have the dual fan. So since it was full dimensional, the fan will be complete. And dP will be a Cartier divisor. So this is what we have. And we want to show the following. I don't know, will we show it completely or particularly in some parts? First of all, dP is ample and base point free. dP, which we constructed here. I didn't say. I didn't say. So suppose that we have a divisor D, and we have its global sections OXD. And we know that it is finitely dimensional, and it gives us a map to some projective space. I write it PS minus 1 since the global sections are given in this way, and so the map is in some, roughly speaking, is given in this way. So the set of global sections gives us a map to the projective space. D is very ample. So this is another definition of very ample, which is from algebraic geometry. If this map I write Xi is a closed embedding. And we say that D is ample if some KD is very ample. Okay, so it should not glue up points together. Very ample divisor means that its global sections will not glue the points together. Примерно понятно в общих чертах? Вот мы хотим что-то такого плана построить.
Да.
Вот. Во-первых, чтобы это было хоть как-то определено, нам нужно, чтобы там не было базисных точек. В каждой точке хоть кто-то не занырялся. Во-вторых, бывает, что на самом деле этих друзей мало. У нас на прошлом семинаре были картинки, где они там все там в две точки склеились. Грубо говоря, если у нас ну, там многообразие большой размерности, а среди этих друзей всего два разных. то оно никак не разделит точки. Мы отобразимся в P1. И что? А мы хотим, чтобы мы получили в качестве образа многообразие изоморфное тому, которое было. Вот. Как бы вот мы будем сейчас бороться за то, чтобы взять кратные дивизоры, от этого станет больше точек, и тогда они уже разделят все и красивенько отобразят нас в изоморфное многообразие. Okay, proposition. If P is a four-dimensional lattice polytope and dP constructed as here, then it is ample and base point free. So it is interesting when n is at least 2. When n is 1, it is not interesting. Then K dP is very n for K at least n minus 1. And the third, which is the most accessible, dP, it is a divisor, it is very ample. If and only if the polytope P is a very ample polytope. What is a very ample polytope? As I said, if I shift each vertex to the origin, then the integer point will generate the whole cone intersected with M. Okay? Okay. What can we say? Okay, should I prove this statement? Доказывать его или пропустим сейчас? Ну, в смысле, как бы, если это некоторым очевидно, а некоторым все равно очень сложно, можно и пропустить. Ananya, do you want to give the sketch of a proof, or is it obvious?
But maybe a sketch, just tell what is going on.
Okay, there are some parts from algebraic geometry and some from combinatorics. Okay. First of all, if we take this divisor and construct back a polytope, it will coincide with P.
В тексте написано это загадочно.
Да, ну написано. Да, в целом это все по боксу, да. Окей. So, first of all, we know that dP is base point free. Just because all might belong to our polytope. So what is interesting? So in fact, we say that there is variety xp here, which is embedded to some big projective space. And in fact, we have our variety xp intersected with M. So we can always say that so if we have this variety, then first we can send it to this one, And then we can send it to P as minus 1. So if we want this to be the closed embedding, then this should be an isomorphism. Because this will be isomorphic to the image of this one. And so it will show that if dp is a very ample divisor, then this will be a very ample polytope. Because how does it work? In each chart, this is just we take these monomials, one of them is shifted to 1 and the others will be shifted to mj minus mi. And so for each vertex, it should be saturated in this sense. Otherwise, it will not be a closed embedding. So in C, it shows that this is true. Now, what if in C, P is a very ample polytope? Then it gives us a closed embedding. By these formulas, it is a closed embedding. So it was the part from algebraic geometry. Now, B is, it follows from the statement, combinatorial statement that I mentioned. Always if a polytope is multiplied by some big k, it becomes very ample. Okay? I said, no. This is always very ample, it can be shown. Okay, what remains? That dp is ample and base point free. Okay. This is a little bit tricky.
dp is ample, it's clear, right? Because n minus 1 of dp is very ample.
Yes. If dp is ample, then the polynomial, one moment, if the divisor is ample, then some multiple is very ample, then it corresponds to a very ample polytope and vice versa. Okay. Now, what about A? So, suppose that P is any polytope. We can always multiply it to make it very ample. So P is any, then we take Kp, which is very ample, then Kdp will be a very ample divisor, so dp will be ample, and if it is ample, it is already basement free. Okay, this is the sketch of the proof. I omitted the algebraic geometry formulas at part C. How do we map varieties to the projective space? Okay, and now to talk about ampleness at the terms of support functions. We need a strictly convex functions. So what is strictly convex? It is piecewise linear at each curve. And when two curves meet, we should have a break. So if phi d, we recall that phi d is given by scalar product with m sigma. So m sigma u equals phi d u if and only if u belongs to sigma. So there are many equivalent formulations of this. So it is equivalent to, for example, phi d u is less than m sigma u for all u not in sigma. What is necessary for us now? This is very important. If sigma prime are curves of dimension n, and sigma intersected sigma prime is a wall, then m sigma is not equal to m sigma prime. Okay? If this is true, then this follows. And if this is true, and we have equality here, clearly it is not true. Okay? It is in the spirit of the beginning of the lecture. If the function is convex, then it is the minimum. And if two m sigma coincide, then the minimum will be the scalar product with the same one, and we will have equality here, and we asked it to be not true. Понятно ли мне сейчас? Я сказала. Можно еще раз. Утверждается, что если функция строго выпуклая, каждый раз, когда мы приводим через стенку, у нас становится меньше, то у нас не могли совпасть никакие m сигма и m сигма прайм, m сигма штрих. Но действительно, если бы они совпали, тогда мы бы получили, что вот берем как бы сигма, а берем u из сигма штрих. Получим, что m сигма u совпадает с m сигма штрих u, совпадает с фи d u. Вот. А мы говорили, что во всех остальных случаях должно быть строгое неравенство вот здесь вот. И наоборот, если здесь равенство, то мы не можем этого получить. Вот. Это, наверное, самое важное, что нам нужно. Okay, this is from convex geometry. There are some other equivalent formulations, but I hope that it is not necessary. So what is very important is the following theorem. I think this will be the last statement of today's lecture. So here we assume that sigma is complete. D is ample if and only if phi d is strictly convex. What does it? Why is it true? First, maybe I say that d and kd, their functions differ by k phi d. So if one is strictly convex, then the other one is, and vice versa. Okay? Если мы функцию на число умножим, от этого ее на положительное число умножим, свойства быть строго выпуклой не поменяются. Okay. First, suppose that B is very ample, so that it gives a closed embedding. While phi B is strictly convex. If M sigma equals M sigma prime, then and sigma is a wall. So it is more or less one case to check. If the function is not strictly convex, then using this machinery we will find two adjacent curves with coinciding M sigma and M sigma prime. I need the proof. If we reconstruct it, we will understand it. Okay. What happens in this case? A very ample divisor is a divisor which gives a closed embedding. Okay? So one of the characters will be chi M sigma. What is clear? If you take U sigma, recall it was the open chart in our toric variety given by the cone sigma. So we had our variety X, which was mapped to the projective space, for example, PS minus 1. If we know that chi M sigma, it is a non-vanishing, it gives a non-vanishing section on U sigma. We can check it just if we take the divisor of chi M sigma plus D. It will not contain the rays of sigma. If rho is in sigma 1, then d rho will be minus a rho plus a rho. Okay? I mean that if I write the divisor, the global section corresponding to this divisor on U sigma, it will be globally defined. Because what is the divisor of chi M sigma plus D? The vanishing locus of a section is given by this divisor. It does not contain prime divisors d rho when rho is a ray of sigma, because it will enter with coefficient minus a rho and then plus a rho, and it will vanish. It will contain only the other prime divisors which are in the complement to U sigma. Понятно? У нас была проверка, где зануляется хи m сигма. Мы ему писали такой дивизор. Дивизор хи m сигма плюс dd, это вот тот, с которым мы работаем. Его надо разложить на простые. Вот. Но, соответственно, когда мы смотрим, с какими коэффициентами оно входит, те лучи, которые входят в сигму, здесь будет значение минус ро, а здесь будет ро, и они умрут. Вот, а дивизоры, которые на у сигма, мы видим те дивизоры, у которых лучи, это лучи сигма. А те дивизоры, которые где-то наружу торчат, они вообще на у сигма не попадают. Мы их и не заметим. То, что они войдут с какими-то коэффициентами это нас никак не волнует, потому что они никак не пересекутся. Поэтому хи сигма будет глобальным сечением на у сигма. Вот. Okay, since chi m sigma is a global section on u sigma, then we can map u sigma to the following affine chart of p s minus 1. It will be a s minus 1, where we divided everything by chi m sigma. Okay? Chi m sigma is not zero. And similarly, we can map u sigma prime to this same copy of a s minus 1. Okay? They have the same m sigma. Let me mention that by the orbit correspondence, the union of u sigma and u sigma prime, it contains p1. So we have a common wall here. The orbit corresponding to the wall will be C star, and the orbits corresponding to sigma and sigma prime will be points on completing this C star. So C star with 2 points, it is P1. Or if you want, if we take the star construction with these two cones, we obtain exactly the fan of P1. Okay? Еще раз, если у нас есть два конуса полной размерности, у них общая стеночка, то в объединении этих двух афинных клеток найдется P1. Хорошо. Okay, now we have this map from the union to a s minus 1. It cannot exist. So it exists, it maps P1 to 1 point. But this is not what we wanted. We wanted it to be closed embedded. And now it doesn't separate points. So this is impossible. I showed that if sigma is complete, then two adjacent m sigma will not coincide, and then phi d will be strictly convex. Up to some technical details concerning strictly convex functions. Okay? Я в общих чертах показала, что если дивизор очень обильный, то соседние m сигма не будут совпадать. Вот. И значит, функция будет строго выпуклая. Okay? And the reverse, if we know that our function is strictly convex, if we know that our function is strictly convex, then we have its Cartier data. We have its Cartier data, and we know that from convexity, we show that P is the convex hull of PD. PD is the convex hull of M sigma. In particular, PD is a lattice polytope. So we have, at the previous seminar, we had the examples when PD is not a lattice polytope. But now, from simple convexity, it is a lattice polytope. And now it is a little bit tricky. First, why PD is of full dimension? It is of full dimension because otherwise, if it is not a full dimension, we can find U which is non-zero from N, and some real number R such that M sigma U will be equal to R for all sigma. Just it will be in some hyperplane, not in the whole space. Then phi d U will be M sigma U. It will be equal to R, and it will not be strictly convex. So we have a contradiction here. So we show that PD should be of full dimension. Okay? Now we have PD of full dimension. And if we forget everything, we have a PD of full dimension with integer vertices. We can construct a Toric variety using it. So PD, we have X P D, it is a Toric variety with an ample divisor, and with the fan sigma PD and normal fan to this polytope. And the PD ample divisor. Okay. We know that if it is ample, then some multiple is very ample, and then it will be strictly convex. So I recall we took a strictly convex function. Okay? Then we have constructed a polytope, and then we have constructed NU fan and then U variety using this polytope. And the divisor is NU convex function. NU strictly convex function. But we know that the old one and the new one will coincide. So we know that phi PD U, it is the minimum when M from PD, the scalar product MU. So in fact, the scalar, the functions phi, which was at the beginning, and the function phi for this divisor, they will coincide. And so, since they're strictly convex, they will have the same curve. The curve is the set when this function is linear. So, in fact, they have the same fence. So, the initial fence where the function phi was defined, it will coincide with the fan for this Toric variety. And we wanted to show that if phi d is strictly convex, then the divisor is ample. Indeed, it will coincide with this ample divisor, so it will be ample. It is the same variety, and it is dpd, so it is ample. We are done. I think that's all for today. Thank you for your attention. Вопросы? Вопросы? Any questions? So then I can я уже все, да? Остальным кто-нибудь заблокировал, я туда пришлю, раз они пришлю. Олег, ну что не надо, его не готов перекидывать. Пожалуйста. А вы тоже даете? Да. Хорошо, можно. А вы что написали в блокировке?
Я написала, что мне не важно.
А?
Я написала, что мне не важно, но лучше, конечно, выучить.
Подождите, а вы какой курс?
Я последний.
А, да, тогда, конечно, тогда нужно. Да.
А можно еще дать сегодня листов?
Да, можно.
Задача 4, 5, 6, там один тоже Вера имеется в виду, да?
Да. Держите. Остальным я когда всем, кто проголосовал, я почему пришлю. Ну, не прямо в секунду.
Можно и вопрос у меня еще?
Да, что вопрос?
Там вот в Коксе есть такое утверждение. Я просто пытался через него сдавать задачи с листочками. Ну, точнее, я не запомнил доказательства из Кокса.
Надо, кстати, это, запись остановить. Как это делается? Сейчас, вот это вот надо сделать?
Сейчас.
Ищи. Так. Остановить, да?